This conference will now be recorded.
So, good evening. Today we'll be discussing refraction at prism, at the surface of prism, and dispersion by prism. So, mainly today's discussion will be on prism. So, prism can do two things. One is refraction, and another one is diffraction. Sorry, dispersion. So, these two things we'll discuss. Before that, we'll learn what is prism and what are the parameters related to prism are important to know. Okay. So what is a prism? Prism is a wedge shaped portion of a transparent refracting medium bounded by two plane faces inclined to each other at certain angle. So prism is made of refracting medium, like it can be made of glass or any transparent medium, plain glass or plain glass or some other glass. I just forgot now. So plain glasses, it is made of mainly glasses. Okay, in the laboratories what we will be using are made of glasses mainly. So look, this is the typical shape of or diagram of a prism. Okay, prism, look, it has three rectangular surfaces and two triangular surfaces. See, this is, see, triangular surfaces are, so two triangular surfaces. Actually, the triangular surfaces are not transparent, not so transparent. These are actually made rubbed somewhat. So they are not transparent. So they are not the refracting surfaces. Okay. So the triangular surfaces are like A, F, E, and another one is B, D, and C. These are the triangular surfaces. So we don't do anything with these two surfaces related to this refraction or dispersion. So the two main surfaces through which refraction happens or dispersion happens are these two surfaces. You can see here we said that two plane surfaces or faces inclined to each other. See, I'll write the plane faces responsible for refraction or dispersion are, see, one is A, B, C, E. This is the one. Okay. Another one is the opposite one. This one. This one. These two opposite surfaces. Okay. Another one is A, B, D, and F. These are two plane surfaces or plane faces which are called refracting surface. These are called refracting surface because refraction happens through this refracting surfaces or refracting faces. Okay. And see, inclined they are inclined to each other by a certain angle. Look, this is the angle. So these are two plane faces. One is, see, A, B, D, F. Another one is A, B, C, E. Okay. So these two plane surfaces are inclined at this particular angle. Okay. that angle is actually denoted by A, so that angle is called angle of prism. Okay, so that is called angle of prism, angle of prism. So the plane faces, they are inclined to each other by an angle, by a certain angle, that is called angle of prism. That is very, very important for refraction. Okay, and the face, see this face DCEF, this is called base. Okay, this is called base of the prism. So this is also a surface which does not take part in refraction, neither in dispersion. This is called base of the prism, base. Okay, and see the line AB, which is actually the line joining the two faces A, B, D, F, and A, B, C, E. So these two faces are meeting at this line. This line is called refracting edge. Refracting edge. Okay, refracting edge. So what are the things we have learned here? There, see, there are two triangular faces and three plane faces. Among them, two plane faces are, or rectangular planes are opposite to each other, and they are inclined at an angle. That angle is called angle of prism. And these two plane surfaces which are responsible for, or the light refracts through these two surfaces, so that's why these faces are called refracting faces. And the line where these two faces are joining there, that line is called refracting edge. Refracting edge. Okay, so these are the parameters we should have learned about prism. And the important thing is, see, when you see in the laboratory, you may see sometime the whole prism like this, and sometime you may not be. See, the prism will be actually using for our practical purpose or our laboratory purpose is actually a portion of this prism, whole prism, a portion of the whole prism. Okay, so if you just chop this up, like see, you just cut like this. Okay, you'll get a triangular shape prism. Okay, look, you will get like this, you will get like this. If it is very thin, then it will look like a triangle only. So if you cut this whole prism by sections, okay, you just cut perpendicular to this AB refracting edge, cut perpendicular to refracting edge, then you will get a shape like a triangle. So that particular prism will be using, and that prism is actually, that section is called principal section. So we'll take the principal section for our practical purpose. And wherever we draw a figure or something like that, or we discuss about refraction or dispersion by prism, we will be drawing a triangle like this to denote a prism triangle. So sometimes this prism can be equilateral triangle, equilateral prism, equilateral. Okay, that means all the sides are equal. Sometime it will be isosceles. Okay, so in that case, two will be isosceles triangle. Okay, so this is a triangle, so equilateral triangle, then isosceles triangle. So in that case, two sides will be equal. Okay, this is how. And now here the angle of prism is this one. angle of prism. These two surfaces are, see, AB and AC. These are refracting faces now. Refracting edges or faces, you can say, refracting surface or face, whatever you say, refracting surfaces. And BC will be the base. This is actually base of the prism. Okay, base of the prism. And what is the A? Angle A. This angle is called angle of prism. Okay, this is called angle of prism. If it is triangular prism, sorry, equilateral triangle, then this A, angle of prism, will be 60 degree. Okay, so this is very important to know. Like, for a prism, whenever you are given a prism for experiment, you will be given two parameters. One is A, another one is mu. Mu is the refractive index, or n, you can say n or mu, whatever. Refractive index of the material of the prism, and angle of prism will be given to you, and then thereafter you have to do the experiments. Okay, so this is, see, you can see from here that light getting incident over here. So this is the normal to the surface, so you can write n prime. Okay, so here m prime maybe. So these are two refracting surfaces, these are the normals, and you can see this is the angle of incidence, this is the angle of, sorry, this is the angle of refraction 1, and this is angle of incidence. Suppose this is R2, and this is the angle of emergence. So you can see this is the emergent ray, this is the incident ray, and this generally this angle is denoted by R1, this angle is denoted by R2, this angle is denoted by E for emergent ray. The emergent ray is making an angle E with respect to the normal at AC surface. Okay, so yeah, so now we'll just move on. So not only refraction, this is for the refraction light. So prism can split the component colors of any light, and that's how it creates a band of various colors of light. Upon passing through a white light, you can see viv. Okay, 7 colors separated out. This is called dispersion of light. We'll discuss in detail again. So prism mainly, we are like, prism is mainly familiar for two phenomena. One is refraction, another one is dispersion. Okay, now we'll just see what happens when refraction happens at the refracting surfaces of the prism, or when a light enters at AB surface and emerges from AC surface, what happens to that light? Okay, we'll see that. So you can see this PQ ray is getting incident at this AB. So the angle of incidence is I here, angle of incidence. Okay, then it is getting refracted through this. Since it is, see, inside the prism there is no dispersion, no refraction, nothing, so it will be parallel to the base BC, and it is directly going to hit the other surface, and upon getting incident over there, it is refracting back to the air again. So here it is air, here also it is air, and here suppose this has refractive index n, okay, or mu, whatever you can think of. Refractive index of the material is n. So there are two refractions happens over here, one at AB surface, AB surface, another one is, or AB interface, another one is AC interface. There are two refractions happens over here, and in between, inside the prism, when light goes from Q point to R point, there is nothing happened, so it travels in a straight line inside the same medium. And we'll show you that this angle of refraction, this one, and angle this R2, they are equal to each other. Okay, and at certain condition, we'll show you that I is equal to E. That means angle of incidence is equal to angle of emergence. So those things we'll be discussing here. All right. So one more point you can see, whenever there is a refraction, I'll just draw another figure, maybe the common figure. Okay, suppose this is air and this is glass. So when light goes from air to glass, light actually bend towards the normal. This is I, this is R. Okay, angle of refraction R. Look here, actually light was actually going like this, isn't it? But it is getting refracted, isn't it? Refracted in this, light gets bent. Refraction means when light enters from one medium to another medium, at the interface light gets bent. So that phenomenon is called refraction of light. So in this case, see, light was actually going this direction, but now getting deviated by this angle. So this angle is called angle of deviation. So what is the angle of deviation? The angle between the original direction, okay, of the incident ray and the direction of refracted ray. The angle between the direction of refracted ray and the direction of the incident ray. That particular angle is called angle of deviation, and that is denoted by delta, angle of deviation. Okay, this is called angle of deviation. You can see here, see, this is a PQ ray. If you just extrapolate it, it will go up to like this. It will go, this is the direction of incident ray. Okay, now what is the direction of refracted ray? This is the refracted ray or emergent ray, ES. If I just trace it back, so it is meeting over here. So these two, so this angle is actually delta or deviation. Deviation is the angle between the incident direction of incident ray and the direction of refracted ray. So that angle is called angle of deviation. So we will see here, angle of deviation has lot of influence on the refraction part. Okay, now we will see, we'll find out relation between angle of deviation. Okay, so mainly we'll be now finding out a relation between angle of incidence. Okay, I have written already here, angle of incidence is I, E, angle of prism, and delta. Delta is the angle of deviation. So relation among, not between, relation among these parameters. Okay, we'll try to find out relation among these parameters. What are the parameters? I, angle of incidence; E, angle of emergence; A, angle of prism; and what is delta? Delta is the angle of deviation. So we'll try to find out relation among these four parameters first. So to do that, let us see this figure. I hope you are able to see it properly. Look here, if I just consider quadrilateral A, Q, N, and R. So this is the quadrilateral which I am just taking now from this figure. Look, this is A, Q, N, R. This is the quadrilateral I am just talking about. So you look here, since this is the normal, this N prime, suppose this one, and N, M. If these are the normal, or already it is written NQ and see NQ, and here NR. These are the normals. Okay, so this is normal to AB surface and NR is normal to AC surface. So look, this angle, okay, this angle is 90 degree. Again, this angle is also 90 degree, because I am saying that QN is normal to QN is perpendicular to AB, and here NR is perpendicular to AC. Okay, so I can write. So from there, what I can write is, I can write AQN, this angle, is equal to ARN, this angle. These are both equal to 90 degree. Okay. Now see, I can tell from this particular inference, from this what I can say, then I can say that angle of prism A plus the angle QNR, that means this angle N and A, this angle, the sum of this angle must be 180 degree, because these are already 180 degree, and for a quadrilateral the sum of the four angles, okay, will be, sum of four angles has to be 360 degree. Okay, and in case of triangle, sum of all three angles has to be 180 degree, right? So in this case, since we have got this angle and this angles to be 90 degree, so angle of prism and angle of this angle N, QNR, must be 180 degree. So from here, okay, so we can get some idea. Now look, another case, consider the triangle, AQR. AQR. From that triangle, what we can say? We can say angle of prism plus AQR, right? So angle AQR plus angle ARN, sorry, ARQ, this has to be actually 180 degree. Okay. Oh, I'm sorry. I have to consider the triangle QNR, not this triangle particularly. Okay, we have to consider triangle QNR. We'll consider the triangle QNR, and from there we'll get some relation between angle of incidence, angle of refraction. See, QNR, this small triangle, I'll just remove this. See, QNR means the small angle, small triangle here. QNR, this triangle. Okay, this triangle, from there I can write R1 plus R2, okay, plus N. N means QNR, this angle to be 180 degree. Okay, now look, one more point over here. QNR plus this angle is, angle of prism is 180 degree. So if I just put it here from, okay, let us say this is equation number 1, this is equation number 2, this is equation number 3. So from equation number 2 and 3, from equation 2 and 3, what we can say, the QNR, we'll just put the value of QNR. So we can put the value of QNR, R1 plus R2, and Q and R I have to write 180 degree minus A, angle of prism, is equal to 180 degree. So if I just do a little bit of simplification from here, 180 degree will be getting cancelled from both sides. So angle of prism will be is equal to R1 plus R2. That means these two angles, sum of these two angles is equal to angle of prism. So what are the things we have got now? So from there, so from here, what we get from all this calculation, what we have got, that angle of prism, simply angle of prism is denoted by A. So this is the thing we have got now. Okay. Now we'll see what is the delta. What is this angle delta? Look, if I just consider the triangle, consider the triangle M, Q, and R. This triangle, this one. Okay, this triangle. These are the vertices M, Q, and R. So this is this triangle if you consider. So delta is the exterior angle. Okay, delta is exterior angle. So exterior angle always will be the sum of the interior angles, right? Okay, interior angles. Okay, so this angle and this angle. So that two, see, this whole angle is actually I. Look, this is I. The whole angle I can say this particular angle is whole angle. This one is I, and if you just subtract this angle R1, look, I am writing. So first angle is this one. Delta is this particular. If I just say X and this is Y. So X is actually angle X is see I minus R1. I hope you will be agreeing. Look, so this is R1. This is whole angle because angle of see this angle is equal to I. Whole angle is equal to I. So this particular X angle will be is equal to I angle of incidence minus R1, and angle of Y will be actually see this is R2. Whole angle is R2, or you can write sorry not R2. This is whole angle is E minus R2. Then you will get Y. Look, I'll just show you once again. This part is alone Y. So this is a whole angle is actually E, angle of emergence. If you just subtract this R2, then you get Y. Okay. So I'll write over here. So it is actually X plus Y. So this X plus Y actually is giving you this plus E minus R2. So if you just take this to near and this you write R1 plus R2. Now I'm giving this equation as 1 and this equation is 2. See look, this R1 and R2, R1 plus R2 I can just put it here from equation 1. So delta is equal to I plus E minus of A. So this is the relation between all these four parameters: angle of incidence, angle of emergence, and angle of prism with delta. Okay. So look what we get. We get that angle sum of the sum of the angle of incidence and angle of emergence is equal to the sum of angle of deviation plus angle of prism. Okay, this is the relation we have got. So I'll just write two equations or two relationship we have got from here so far. A, angle of prism is equal to R1 plus R2, and delta equal to I plus E minus A. So these are two relationship I have got if I give these two 1 and 2 relationship. Okay. So from here, look, what are the factors on which the angle of deviation depends on? So angle of deviation depends on this, angle of deviation depends on this, angle of deviation depends on this. Okay. So we'll write one by one. So factors on which angle of deviation depends. Okay, so factor number one, that is, I'll start from here. So factor number one, that is the angle of incidence. Angle of incidence. Okay. Then second factor, the materials of the prism. That means refractive index. So angle of deviation depends on material of the prism, whether it is made of glass or something else. Prism, that means it actually material has a particular refractive index mu. So it depends on mu or n, whatever you say. So material of the prism. Then angle of deviation depends on color or wavelength. Depends on color or wavelength of light. Okay. And the fourth point is actually it depends on angle of prism. Angle of prism. So these are the four parameters on which the angle of deviation depends on. Okay, you have to remember these points because sometimes there will be competitive, like in the competitive exam or in the board exam, there will be a multiple choice type question depending on these informations. Okay, so factors on which the angle of deviation depends are angle of incidence, then angle of prism, material of the prism or refractive index of the material of the prism, color or the light, sorry, color or the wavelength of the light. Okay, so these are the parameters on which angle of deviation depends on. Now what we'll see how angle of deviation angle of deviation vary with angle of incidence. That means we'll see a graph delta versus I, angle of incidence versus delta, or sorry, delta versus angle of incidence, that is angle of deviation versus angle of incidence. So what we can see from here, we can see as the angle of incidence increases, this way angle of incidence increasing 0, 20, 40, 60, etc. As angle of incidence increases, the angle of deviation starts from here, so it is actually decreasing. And till what point it is decreasing? Until it becomes minimum at certain point here. So delta becomes minimum at certain point where angle of incidence equal to angle of emergence. Okay, where angle of incidence equal to angle of emergence. So delta, so angle of deviation, I'll write deviation becomes minimum at I is equal to E when angle of incidence becomes equal to angle of emergence. That time delta becomes delta minimum, and thereafter if you increase your angle of incidence, then angle of deviation again increases further like this. Okay, so you can see another point, very interesting point, that for this delta versus I curve, For a single value of delta, see this is suppose 50-degree delta. For a single value of delta, you are getting two angle of incidence. One is, see this one I, another one is E prime. Okay, understand what I'm trying to say? You have two angle of incidence corresponding to, so two angle of incidence, two angles of incidence corresponds to a single value of delta. For a single value of delta, delta is 50 over here, but how many angle of incidence you get? One is here below 40, another one is here below 70 maybe. Sorry, below 80 or around 70. You look here. Okay, there are two angle of incidence. What does this mean? This means, see, one is I, another one is E. That means one angle is angle of incidence, another one is angle of emergence. And see, if you just do so, and this is actually the angle of, see, refraction process. We have seen refraction is actually reversible phenomena. That means you have a light, you have interface between air and glass. Okay, light goes from air to glass like this. Okay, when it goes like this, it goes. Okay, now if you want to do the reverse way, the experiment reverse way, that means you just pass your light from glass to air, the deviation will be the same. Deviation will be the same. That means what? The angle of incidence here becomes angle of refraction, and here angle of incidence become, sorry, angle of refraction becomes angle of incidence. And see, the angle of deviation remains the same. Okay, angle of deviation I just explained you, right? So angle of deviation remains the same for both way. If you do the reverse way also, you will get the same angle of deviation. So that's why for a single angle of deviation, sorry, yes, single value of angle of deviation, you get two angle of incidence. That means one you can treat as angle of incidence, another one you can treat as angle of emergence, or vice versa. This process is reversible. You can start from AC surface, and then light will emerge out from AB surface, or you are starting generally AB surface, from AB surface, and light is emerging out from AC surface. But angle of, see, this angle of emergence and angle of incidence may not be equal always. Only when angle of deviation is minimum. Only when angle of deviation is minimum. Look here, at this particular point, angle of incidence has only one value. That means your angle of incidence and angle of emergence, they become equal. Okay, only at the angle of minimum angle of deviation of the prism, angle of incidence and angle of emergence become equal. Okay, they become equal. All right, so we have learned what is angle of deviation, what is minimum angle of deviation, and at minimum angle of deviation what happens, we have learned already. So at minimum angle of deviation, so what we get at delta m, delta equal to delta m, we get I is equal to E. Angle of incidence is equal to angle of emergence. Okay, so at this condition, look what we can write. We had got a relationship. We have got a relationship between delta is equal to I plus E minus A. This is what we have got. So this E I can write as I. Okay. So at minimum delta. Okay. So del minimum is equal to I 2I minus A, or I, angle of incidence I can find out at this particular minimum deviation condition of prism, I can find out what is the angle of incidence. So delta m plus a divided by 2. So this is what I can find out from here. So at minimum angle of deviation, I have got angle of incidence. Okay, I'll write it clearly here what I have got. So for minimum angle of deviation, we can find out angle of incidence. Now we'll try to write the Snell's equation. Maybe I'll just go to the previous slide. I'll just try to write Snell's Snell's law for this two surfaces, okay, two interfaces, or maybe at one. Okay, anyway, no problem. So let us see what is the Snell's law. We know n1 sine of angle of incidence is equal to n2, the refractive index of the second medium, sine angle of refraction. This is what we are trying to now write for this prism. So see from here what we have got. We have got angle of incidence, as I said, we get angle of incidence as delta minimum plus a angle of prism divided by 2. How? From here, I plus e minus a is equal to delta minimum. So from here, if you just do that, you will get this relation. So what we have got already, we have got what is I. So n, refractive index n, suppose this refractive index of air medium n. Okay, so air medium is n, n1 I can write sine I is delta minimum plus a divided by whole divided by 2. So this I have got. Now I have to find out what is angle of refraction. Look, I have got one more thing over here. So when at the angle of minimum angle of deviation, one more thing happens. What happens? See, this light inside the prism, light becomes parallel to the base. The QR is parallel to base at this minimum at delta m. That means what? This particular angle R1 and R2 equals to, so this implies that R1 is equal to R2. Okay, this becomes equal. All right. So this R1 is equal to R2. Okay. So and if you remember in the equation number 1, what we have got, R1 plus R2 is equal to A. Look here, we know R1 plus R2 is equal to A angle of prism. So if we know these two are equal at minimum angle of deviation of the prism, then I can find out what is R1. R1 will be becoming, see, R1 plus R2, so I'll write 2R1, so A by 2. So I am just writing the Snell's law for AB surface, Snell's law for the interface AB, for interface AB. I'm writing for that. So one side is air which has refractive index n1 suppose, and this medium of the prism it has n2. Okay. So at this AB surface I am writing. So what I have got? I have got angle of incidence, that is, see, delta minimum plus, so minimum deviation, angle of deviation plus angle of prism divided by 2, that is the I. I have got already delta m plus a by 2, and R1 I am getting from here now a by 2. So I have got I have got angle of incidence, angle of prism, sorry, angle of, yes, angle of refraction. Then there is no bar to write the Snell's law. If I know the refractive indices, or if I don't know, I can find out the refractive index of the material of the prism, because for air it is 1. See, look, I'll write it directly. See, for air it is n1 is equal to 1. I'll directly write here n2 is equal to n, or I'll write n2 is equal to mu maybe. So mu sine R1 here. Okay. So this is I, this is R1. So mu sine R1 means A by delta by A by 2. Okay, from here. Now from here, see how we can find out mu, or refractive index of the prism, that is sine delta minimum plus A divided by 2 over sine A by 2. So this is the relation between minimum angle of prism, minimum angle of deviation, angle of prism, refractive index. So this particular relationship will give you the relation between the refractive index of the medium or the material of the prism, minimum angle of deviation and angle of prism. Okay, so this is the relation you should remember. I'll explain everything and what we got we'll write. So this is a relationship you should remember in general. But there is a special case. We'll write a special case. Okay, what is the special case? If angle of prism, if the angle of prism is very small, okay, if the angle of prism, that means A is very small, and also angle of deviation delta minimum is very small, then what we can write? Sine theta we can write as theta. Okay, so I can write mu is equal to, see, I'll just do the calculation left hand side and write the final answer. So look here, I'll write. So what I can write, if both angle of deviation and angle of prism are very small, for that case what will happen? Mu will be, see, sine theta is equal to theta, so I can write delta m plus a divided by 2 whole divided by 2 here, sine a by 2, sine a by 2 will be equal to a by 2, 2 goes off, and if you do the calculation, see, I'll just write here mu into a minus a is equal to delta m. So from here I can find out what is the minimum angle of deviation if you know the angle of prism and refractive index of the medium of the prism. So suppose, so as I said in the beginning itself, in your experiment, what will be given? In the beginning of the experiment, you will be given a prism and you will be given two parameters. One is angle of prism and refractive index of the medium. So from there itself, you can just directly calculate what will be the angle of minimum deviation. And we have to do all the calculations at this condition, angle of minimum deviation, because as we had seen, at angle of deviation, angle of emergence and angle of incidence will be same. Otherwise, you will be confused with two angle of incidence. Okay. All right. So what we have got? We have got a relationship between minimum angle of deviation, angle of prism, and the refractive index of the material of the prism. And if the angle of deviation is small, very small, and angle of prism is also very small, angle of deviation this one, angle of prism is also very small, in that case we can make an approximation and we can find out what is the angle of deviation. This is the relation. So these two relations, this is actually general formula, this is the special case formula, you should remember. It implies that, so from this formula what we can understand, see here there is no dependence on, see, no dependence, no dependence of angle of incidence on delta. Okay, that means light does not deviate much depending on the angle of incidence. Okay, so this is the implication we get from here. The minimum value of the angle of deviation a, at the minimum angle of deviation, a ray on passing through a prism will actually pass through with this like having same angle of emergence. So the minimum value of the angle of deviation suffered by a ray on passing through a prism is called the angle of minimum deviation, and that is denoted by delta m that we have already discussed. So yeah, so from here I can just give you few special cases regarding this formulas. Okay, so you have got when the angle of deviation will be minimum, but when the angle of deviation will be maximum, what is the condition for that? To get maximum angle of deviation, what is the condition for that? Condition for that is actually, see, delta max is equal to 90 degree plus I prime, I prime in the sense angle of emergence. This. So when your angle of incidence is 90 degree, when your angle of incidence is 90 degree, then your angle of deviation will be maximum. Okay. So deviation produced by a prism will be maximum when the angle of incidence is 90 degree. You can remember this for your competition exam. So angle of deviation, we have seen angle of deviation is minimum only for only one value of angle of incidence. Okay, that is equal to the angle of emergence. So this is what we have seen. Okay, all right. So I think this is all with the angle of deviation and refraction through. So this is actually the part of refraction. This part was refraction by prism. Now we'll see dispersion by prism. Okay, we'll see dispersion by prism. Dispersion by prism, I will not take too much time, maybe another 15 minutes, and then we'll conclude the lecture. Be patient, Deepa. Yeah. So dispersion of light. What is dispersion of light? This you might be little bit familiar with from your previous classes. When a white light or sunlight passes through a prism, it actually gets splitted into its constituent colors. And as you can see, you will see the order of the colors, and constituent colors will make a spread of colors. So spread of color, this spread of color, so this is, suppose this is red, this spread is called band. This particular thing is called band. So you will get band of each colors, band of each colors. So this bands of each color, when you see in the screen, this is called spectrum. Spectrum, you see band of colors, that is called spectrum. Okay, white light spectrum, this is white light spectrum. And you can see the bands of light from below. If you see, it will be violet, indigo, blue, so violet, indigo, viv green, yellow and red. Okay, orange and red, viv. Seven colors, 1 2 3 4 5 6 7. Okay, 3 and 1. Okay, so viv, violet, then indigo, then blue, green, yellow, orange and red. Okay, so these are, this is the order of that. Okay, so look, as a definition, what we can write, what is dispersion of light? The phenomenon of splitting of light into its component colors on passing through a refracting medium is called, not only prism, you can get at any refracting surfaces, you can get splitted with. See, if we have done refraction with polychromatic light, polychromatic means monochromatic, means only one color or one wavelength will be there in the light. So if we see with polychromatic light, refraction through any interfaces will give you multiple color bands. Okay, so here in the prism it is very prominent, and this is the famous experiment was done by Sir Isaac Newton. He had contributed lot to the classical mechanics, to the calculus, in the mathematics, and many other fields, as well as optics. Okay, ray optics, in the part of ray optics he has contributed a lot. Okay, so this is the dispersion of light, splitting of, mainly splitting of light into its constituent color is called dispersion of light. And why it happens? Actually, in the very beginning, people were little bit confused whether the color is obtained by the prism, obtained from the prism, or prism has the property to split the white light or polychromatic light into different colors. So to refute that, or to confirm that, Sir Isaac Newton has done the famous experiment. This is the reverse experiment. You look here, the reverse experiment. What is this reverse experiment? He had taken exactly same or similar prism and put it inverted way. Okay, look, the base is here in this case for the second prism. So when the light is getting incident on the first prism, it is actually, it is getting splitted into different color, and that those emergent lights are made to fall on the refracting surface of the other prism, and when it emerges from the opposite surface of the second prism, all the lights recombine to give you white light. So this is what is proving that prism is not giving the light to prism is not giving the colors to the light, but it is splitting the light into its components. Okay, so in the nature we see the evidence of, like, see, rainbow is one of the r- result of atmospheric dispersion. Atmospheric dispersion, see, this is atmospheric dispersion. Atmospheric dispersion. Okay, what happens over here? Look, sunlight, this is a raindrop means you have water molecules here, water, this is a water droplet or rain droplets, raindrop, one drop. So you have air outside, inside the water, isn't it? So this surface of the raindrop is actually becoming an interface for refraction, and this is a transparent medium. So sunlight comes and get refracted at this surface. In fact, it is getting dispersed. Dispersed means what? It is split into different colors, and when it, all the light goes here on the opposite face, luckily, by nature, what is happening? The angle of incidence is becoming greater than the critical angle IC. And what is happening over here? TER, total, TIR, total internal reflection, and then getting back to this space. And here again refraction happens. So rainbow is formed due to three fundamental phenomenon. One is dispersion first. Here dispersion happens. Dispersion. Okay. First dispersion happens. Then what happens? Total internal reflection, TIR, and then again refraction. So these are the three sequence. So these are the sequence. And this kind of refraction, so when there is only one total internal reflection for the same light, one only for one light or one ray, then it is called primary rainbow. This is called primary rainbow. Primary rainbow. Okay, this is called primary rainbow. Okay, when only one TIR happens. Okay, now look, when there will be two internal reflection, in this case light is going like this, so one internal reflection here, TIR, another TIR is here, so two total internal reflection. So look, dispersion, then dispersion, then TIR, another TIR, and then finally refraction happens. So this are the sequence. Okay, so this is how. And see, when this splitted lights comes to our eyes, we see multiple colors like this. Okay, vivid here we see. So this is how rainbow forms. Okay, so I'll just take another 5 minutes to discuss one important topic over here. This is very important. Dispersive power of prism. Dispersive power of prism. Okay, I have not told you what is the reason for dispersion. It is actually, see, when you have the refractive index, this depends on color. Okay, wavelength. So when you have multiple colors, they have different wavelength, red and violet. So refractive index becomes different for different color of the. So I have glass, but when I use this glass to conduct a refraction by red light, then the deviation of the red light will be different, because the red light has greater wavelength, and refractive index actually is inversely proportional to this. And also refractive index is inversely proportional to the velocity of the light inside the medium. Okay, so red light will be having greater velocity than the violet light or other colors inside the prism. That's why deviation of the red light will be least, and deviation of the violet light will be most, because it has the lowest wavelength. That's why the speed will be very less inside the prism, and because of the difference in the speeds, the deviations also will be different, and that's why they will not combine to each other, rather they will be splitted from each other. Okay, so this is the reason for dispersion. Okay, let us discuss this dispersive power. Dispersive power means how much a prism can disperse or deviate a light, okay, from its original path. Actually there is a formal definition. First look here, when white light comes, it after passing through the prism, it actually actually splitted into constituent colors, and there are all colors in between. This is the violet and this is the red, and it says that yellow is the mean color. Mean color. Okay, mean color, that means it is between, exactly between red and violet. This Y means yellow. So yellow color is the mean color. So this is the mean color. You look, mean color means it will be exactly between these two. And as I discussed, red will be having less deviation. So see, this is the deviation, angle of deviation of the red light, and this is the angle of deviation of the violet light, and this is the angle of deviation of the white light. yellow light, medium yellow. So yes, now see, angular separation between two extreme colors, violet and red, is called the angular dispersion. First of all, you need to know what is angular dispersion. Angular dispersion. So angular dispersion is actually the angular separation between the extreme two rays. One is, so angular separation, this one. So angular separation, this is the angular separation between these two lights. So look here, angular separation between these two lights. So this is the deviation. See, this is the one. This is the angular separation, which is delta V minus delta R. This is called angular dispersion. So angular separation between the extreme two light is called angular dispersion. So we have got angular dispersion. Now, what is dispersive power? So see, we have already learned one more thing. I need to write over here. See, we have delta red. We can write mu r minus this into a, and for yellow I can write mu, simply mu I can write this is the refractive index of the yellow, or the mean color, and delta V is the mu V refractive index. So this is refractive index of the glass for the light, red light. This is the refractive index of the glass for the violet light, and this is for the main color yellow. So these are the formula we have already learned, right? See, minimum deviation, angle of deviation, from here we have got this formula, right? So delta M is equal to mu minus 1 into A. So from there I am writing over there for different colors. Sorry. So for different colors over here. Now see, if I just do this del V minus del R, so what we'll get, if you just do that, you'll get mu V minus mu R, okay, into A. This is what you get. All right. Now we'll write the definition of dispersive power. So we have got angular dispersion. Now we'll write what is dispersive power. It is actually defined, see, it is defined as the ratio of angular dispersion to the mean deviation, So what is mean deviation? Mean deviation was delta YOLO, that is mu minus 1 into A. Okay, mean deviation was the deviation, angle of deviation for the mean color, that is YOLO, which we have taken as this one. Okay, if we put these things, we'll get angular deviation. We have got mu V minus mu R into A, and here we have got mean deviation is mu minus 1 into A. If we just strike this out, so we'll get this one, mu V minus mu R divided by mu minus 1. So this is the dispersive power. So this is the dispersive power. So you will be getting very many questions from this dispersive power also, for like in your board exam or maybe in your competitive exam also. So I took little extra time, but it was worth learning. So Deepa, if you have any question, you can ask me today or maybe sometime else also. So this is all for today. We have learned a lot of things related to dispersion or refraction through prism. So do you have any doubt?
No, sir.
I don't listen to you. Actually, can you write in the chat box? Otherwise, okay. So if you don't have any doubt, I'll stop it here. But if you get any doubt, you can ask me anytime else also. Okay, very nice. Very nice. So it seems all doubts are clear. All right. So we'll stop it here. Bye for today.